Hi everybody. Today's video is going to be on 7.3 Trigonometric Substitutions. Okay. So in this section, we're going to tackle integrals of a very specific type. So often, the following radical, let me write it this way, plus or minus a squared plus or minus x squared appears in an integral. Which can be difficult to work with. Okay, so a lot of times we have this radical and it just appears in an integral, and without the following technique that we're going to learn, there is no other way to solve these things. And this is a very powerful technique that we're going to determine, okay? So we're going to be doing a substitution a little bit different. So in this section, instead of letting u be some function of x, we let x instead be a function of theta. Okay. Now, this is different. Instead, so what we're actually saying is we're saying instead of calling some new variable a function that we see, we're actually taking our old variable and turning it into a function. This is just as legal as what we were doing before. So this is effectively just a substitution. Now, if you do dx, then if you do x equals g of theta, then this means that dx is g prime of theta d theta. And so this means that when you have an integral that looks like this, f of x dx, this becomes the integral of f of g of theta and then g prime of theta d theta. In other words, it looks like the u substitution but going the other way. Now, it seems like you'd be making things more complicated, but the idea is that we're going to choose a function g that makes our lives easier. In other words, this guy is going to be easier integral. This guy's going to be our easier integral. So it all depends on what f is and what g you pick, right? We're trying to pick something where our goal, as you're going to see, is going to be to make that radical go away. Let me give you an example. Not a full-on example. I just want to say, for example, if the square root of 4 minus x squared appears in an integral, we can use the substitution x equals 2 sine theta. Pretty bizarre, right? That we are letting x be a trig function. It seems like we would be making this more complicated, right? So why would we do this? Well, let's see what square root of 4 minus x squared becomes if we replace x with 2 sine theta. This guy would be the square root of 4 minus 2 sine theta squared, which is equal to the square root of 4 minus 4 sine squared theta, which is equal to the square root of, I can factor a 4 out, and I have 1 minus sine squared theta. And isn't 1 minus sine squared the same as cosine squared? And so finally, what does this equal? This actually equals 2 times the absolute value of cosine theta. So all of that stuff that we did, right, just by replacing x equals 2 sine theta, we actually ended up getting rid of the radical, right? There is no radical. This is a big deal. Now, there is something I want to say here, right? You may wonder, what about this absolute value? Doesn't that make things complicated? Well, in an indefinite integral, we tend to ignore the absolute value, okay? But for definite integrals, you do need to use it since you're going to be plugging numbers in. So let's just say this on the next line. So note, in an indefinite integral, we can ignore absolute values of trig functions. Right? Because we're not plugging a number in anyway, so we can just essentially assume that what we're going to be plugging in will make it positive, right? But that's not always true, of course. So for definite integrals, right, for definite integrals, the absolute value must be used. Otherwise, you're going to get the wrong answer. Must remain. Okay? Now, what we just saw is a typical example of what we call a trigonometric substitution, or trig substitution for short. So, what are the useful identities that we need? So, useful identities. You may remember these from the last section because we use these both quite a bit. But remember, we have sine squared theta plus cosine squared theta is equal to 1. And we also have tan squared theta plus 1 is equal to secant squared theta. So let's think about what this means, okay? If you have a radical a squared minus x squared, then you're going to let x equal a times sine theta. This is an example of what we just saw, right? The reason why we let x equal 2 sine theta, if we go back to our problem, we let x equal 2 sine theta because 2 is the square root of 4, right? That's why it worked in this problem, because we knew we were going to square it. So the idea is that we want to use the Pythagorean identity to get rid of the radical. So you can let x equal a sine theta. What about if we have square root of x squared minus a squared? So now letting it be sine is not going to help, okay? We need to use secant theta. Why secant? Because now x takes on the hypotenuse, right? So x takes on the hypotenuse. Finally, what happens if you see a plus sign, okay? So what if you see a squared plus x squared? Then this means that you're going to let x equal a times tangent theta. Okay, because 1 plus tan squared is secant squared. So let me again write down what's happening here, okay? You're going to end up, in this case, you're going to end up using 1 minus sine squared theta is cosine squared theta. For the second problem, you're going to end up using secant squared theta minus 1 is tan squared theta. And in this last one, you're going to end up using 1 plus tan squared theta is equal to secant squared theta. So that's the idea. However, let me give you a more general substitution, okay? Because sometimes you'll get problems that are even more challenging than this, where we don't see a nice thing like that under the radical. So let me give you some more general guidelines. So, more general guidelines. So if you see an a squared minus some function squared, then your substitution, let me create a little table here. Your substitution is going to be f of x is equal to a times sine theta. And the identity that you're going to use is 1 minus sine squared theta is cosine squared theta. So this is what appears in the integrand, okay? So this is our little table here. So that's our first one. In our next one, if you have f of x squared minus a squared, then your substitution is going to be a times secant theta. And again, the identity that you use is secant squared theta minus 1 is equal to tan squared theta. And then finally, if you have a squared plus f of x quantity squared, then you're going to let f of x be a tan theta. And so this is going to become 1 plus tan squared theta is equal to secant squared theta. Okay, now there are two things I want to say here. So we'll call these warnings, okay? Or let me just call these tips, okay? So, well, the first one's a warning. I'm going to call it a warning, because this is something that students always do wrong, okay? So first off, don't forget to find dx. I cannot stress this enough, okay? People will do this trig substitution and they'll completely forget about the dx. You need to convert the dx also. Okay, so every example we do, we're going to do the dx as well. Now, another tip, this one I'm going to call a tip. You can turn any quadratic expression into this form. Okay? So this is what we are talking about here. You can turn any quadratic expression into this form by using something called completing the square. And so in our hardest example that we see, we're going to see a case where we do have to do this work first before we go ahead and do the problem. Okay, so one more thing I want to say here. So note, one more thing I want to say here. Note that when changing, so let me just say one thing, sorry. After integrating, use your original substitution to create a triangle to assist in changing back to the original variable. So as an example, what do I mean by this? So let's say that you let x equal 2 sine theta, right? If you let x equal 2 sine theta, then this means that sine of theta is equal to x over 2. And so remember, sine is opposite over hypotenuse. So this would be your opposite, and this would be your hypotenuse. And so you can go ahead and draw a triangle here. You can draw a right triangle, and you could call this guy theta. And then that means that the opposite is x, the hypotenuse is 2. And then you can use the Pythagorean theorem to find this, right? This would have to be 4 minus x squared, right? And then I could say, use this triangle to change all thetas back to x's in your answer. Okay, so this is the general process that we're going to be using in order to solve trig substitution problems. So let's do some examples now. Okay, so let's do our first example. So example 1, we're going to integrate 1 over t squared times the square root of t squared minus 16 dt. We notice that there are no u substitutions that we can do in order to help us solve this problem, right? We don't see any derivative that appears on top that could help us here. So we are going to instead use a trig substitution. So we notice that we have a t squared minus 16 in there. Okay? Remember what we said. If we see t squared minus a squared, then our substitution is t is equal to a secant theta, right? So what is a in this problem? We actually have t squared minus 4 squared, don't we? Because 16 is 4 squared, which means that we're going to let, so let me write it here, let t equal 4 secant theta. 4 secant theta. Now, before we go ahead and replace t with 4 secant theta in our problem, we need to immediately write down what dt is, okay? That way we won't forget to do this. So dt is equal to 4 secant theta tan theta. All I did was take the derivative, right? The derivative of 4 secant theta is 4 secant theta tan theta, d theta. So now we're going to replace every t that we see in our integral with 4 secant theta, and we're also going to replace dt, right? We have this guy right here, dt. We're going to replace it with this. So let's see what we get here. We have to be really careful with our algebra. So we have 4 secant theta squared times the square root of 4 secant theta squared minus 16, and then our dt is 4 secant theta tan theta d theta. Okay, that may look really complicated, but I promise this is going to become a lot easier once we simplify. So let's go ahead and do that. First of all, the top is just 4 secant theta tan theta. What's the bottom going to equal? Well, if we square that, we get 16 secant squared theta. And then what's under the radical? Under the radical, we have 16 secant squared theta minus 16, right? Let's look at just this radical, okay? Just this radical. If we bring it over here, or let me deal with what's under the radical, right? 16 secant squared theta minus 16. I can factor out a 16, and I get this. But then this is the same as secant squared theta minus 1 is the same as tan squared theta. So if I were to take the square root of this, what would the square root be? It would be 4 times the absolute value of tan theta. However, remember, it's an indefinite integral, so I'm just going to write it as 4 tan theta. Okay, so here's what I get. 4 secant theta tan theta, and on the bottom I get 16 secant squared theta, and then I have another 4 here, 4 tan theta d theta. You can probably notice we can cancel a lot of stuff here. So let's go ahead and do that, right? 4 tan theta goes away with a 4 and a tan theta. And then we have a secant theta on top, which is going to go away with one of these secant thetas on the bottom. And so we're left with the integral of, now what does a secant on the bottom really mean? This is actually just a cosine theta on the top, and I'm going to pull this 1/16 out. So this is what we get, right? This is a very easy integral to do. So now we can actually integrate it. This is going to become 1/16 sine theta plus c. Am I done? Can I leave that as my final answer? The answer is no, because we have theta and we need to change back to t, right? So this is what I was saying about using our triangle, okay? Now I want to look at this original substitution here. We let t equal 4 secant theta, which is the same as secant theta equaling t over 4. Okay, what does it mean for secant theta to be t over 4? Remember, secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So this is actually hypotenuse over adjacent. So if we were to draw a triangle to help us change back, there's our triangle. There's theta. The hypotenuse is t, and the adjacent is 4. So then this guy would be t squared minus 16. Okay. By the way, it is not a coincidence that this missing side of the triangle that we filled out is equal to that radical that we got under the square root. That is always going to happen in these problems. In many ways, this is your check to make sure that you use the identity correctly in the beginning. Okay, so what do we do now? Well, now we know what sine of theta is, right? What is sine? Sine of theta is going to be opposite over hypotenuse in that triangle. And so if you look at the triangle, you just write down its opposite over hypotenuse, and this becomes my answer. The opposite is square root of t squared minus 16, and the hypotenuse is t. So 1/16 times that, I could just write my answer like this. Let me make this a little nicer here. There you go. So that's our answer. Yes, you could check this answer by taking the derivative and make sure you get what you started with. And remember, you would have to actually use the quotient rule for this to take the derivative. This method is actually quite simple as long as you remember your 3 substitutions that you're going to make. Okay, so that's the key to all of this. The key to all of this is understanding how you're using these identities and manipulating stuff so that the radicals will go away. It goes without saying, before I do another example, you need to be extremely comfortable with trig functions for this section, right? You're going to be doing lots of trig integrals. So again, memorize those important ones that I said earlier in the last section. Okay, let's do another example here. This is number 2. We're going to do the integral of t to the 5th over the square root of t squared plus 2 dt. Okay, so we notice that we have a t squared plus 2, right? And remember, we know that if we have t squared plus a squared, we know that we're going to let t be a times tan theta, right? What do we have in our problem here? We actually have t squared plus the square root of 2 squared, right? Because 2 is not a perfect square. So this means that we're going to use the square root of 2 times tan theta. Okay? All right. So, again, always find dt right away. So what's the derivative of tan theta? It's secant squared theta, right? So we're going to get this. So now we're going to replace dt with this, and we're also going to replace every t that we see with square root of 2 tan theta. So let's see what we end up with after our transformation here. If we raise t to the 5th power, what do we get? What's the square root of 2 to the 5th power? Well, you know what? I'm just going to write it this way for now. I will tell you guys what we get in a second, okay? So we get square root of 2 to the 5th power, tangent to the 5th power. And then let me write down our dt. dt is square root of 2 secant squared theta. Here's our d theta. And then our denominator is going to be the square root of, what is t squared? If you square the square root of 2 tan theta, I get 2 tan squared theta and then plus 2. I like to usually take this guy and do this separately, okay? So what's that radical going to become? If I factor a 2 out, I get tan squared theta plus 1. And then this square root of 2 can pull out, and then we have the square root of, actually, let me write it this way. This is just going to be 2 times secant squared theta, right? Because tan squared theta plus 1 is secant squared theta. And then finally, this becomes root root 2 times secant theta. Now remember, this is an absolute value, but we get to ignore the absolute value. You know what? Let me just write it in, but we're going to ignore it because this is an indefinite integral. Okay. So let's see what we get here. How many square root of 2's do we have on the top? We have square root of 2 to the 6th power? Or you know what, let me write it this way. We have tan to the 5th theta, secant squared theta, then we have another square root of 2, and then on the bottom, we now have a square root of 2 and a secant theta. So can we cancel some stuff? Yes, we can, right? We have a square root of 2 that goes away, and we also have one of our secants that goes away, right? So we have this. What is square root of 2 to the 5th power? So square root of 2 to the 5th power. Here's a way to look at it, right? Square root of 2 times 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 square root of 2. This gives you 2. This gives you 2. So really, it's 4 root 2. Okay? So here's what we get. Let's go on the next page here. We have 5 tans and 1 secant, right? So we have 4 root 2 integral of tan to the 5th theta secant theta d theta. Let me make sure I didn't write that incorrectly. I think I'm okay so far. So I have 5 tans and 1 secant, right? Okay, so we actually have this integral now, and for those of you that have finished your 7.2 homework, you recognize this as an integral that we know how to solve, right? In particular, we know that if the number of tangents is odd, then we know that we're going to be able to peel off a secant and a tangent, right? So this becomes tangent to the 4th theta, and then I have secant theta, tan theta, d theta. And I know I need to convert those tangents to secants. So I know that secant squared theta is equal to, let me write it this way. I know that tan squared theta is equal to secant squared theta minus 1. And so I know that if I square both sides, then I get tan to the 4th theta. So this is what I get. And now I'm ready to do my U sub. Yes, I'm doing a second substitution in one problem. So I'm going to let U equal secant theta. And du, as we know, is secant theta, tan theta, d theta. So this gives me u squared minus 1 squared du. And we now have something algebraic that we can solve. So let's go ahead and do that. First, I'm going to square the inside out. I get u to the 4th minus 2u squared plus 1 du. So this gives me 4 root 2 times 1/5 u to the 5th minus 2/3 u cubed plus u, all plus c. But we are not done, right? Because we need to convert everything back to x. And I don't want you to forget our transformation. We actually went from x Oh no, sorry, we started with a t, didn't we? Yes. So we went from t to theta to u. So now we need to go all the way back step by step. So this first guy going back is not that bad because u is equal to secant theta. So that means that we have, so let me go to the next page here. We have 4 root 2 times, so we have 1/5 secant to the 5th theta, and then we have minus 2/3 secant cubed theta, and then we have plus secant theta, and then plus c. From here, I now need to change theta back to t. And for this, I'm going to use my triangle that I have to create. So let's go back to what our original trig substitution was. Notice that we had right here, t is equal to the square root of 2 tan theta, right? So that means that, let me do this over here. Tan theta is equal to t over the square root of 2, right? So tan theta is equal to t over the square root of 2. So if we were to draw our triangle here, and there's theta, remember tangent is opposite over adjacent. So this becomes t square root of 2, and then this is going to become the square root of t squared plus 4, right? Oh no, sorry, t squared plus 2. Which, by the way, let's go ahead and highlight that. That should match this, and it does, right? It matches the original thing that we had in the square root, so this is a good sign. Okay, so notice that this says secant. We have a bunch of secant theta here. So what would secant theta be according to this triangle? Remember, secant is hypotenuse over adjacent. So it's going to be square root of t squared plus 2 over the square root of 2, or another way to write that is just t squared plus 2 over 2 to the 1/2. Okay, so this is how I would write my answer. I would write it this way. Four root 2 times 1/5, and I'm going to raise that to the 5th power. So t squared plus 2 over 2 to the 5/2 minus 2/3 times t squared plus 2 over 2 to the 3/2, and then plus t squared plus 2 over 2 to the 1/2 plus c. Everything I wrote here is my answer. Yes, there is maybe some extra simplifying we can do just because we have 2's in the top, 2's in the bottom, things like that, but this is okay. I'm going to leave my answer this way, okay? This would be my unsimplified answer. Okay, hopefully that made sense. I'm going to keep going, and this is going to be a more complicated example, this next one. So this is number 3. I'm going to do the integral of x squared over the square root of 9 minus 25x squared. Okay. Now, the complicated thing about this is that we have a 25 there, right? We have an extra number there. So this is what I was saying. Remember, I gave my general form here. We have a number squared minus a function squared, right? This is what we have. So this is what we have. And I want to remind you guys, we actually had one of these. We actually had one of those as well, this was one of the cases that we considered, right? So if we go back, we notice that we have the first case, don't we? So it says that we're supposed to let f of x, it's the top case, right? We want to let f of x equal a sine theta. So if we come back to here, we know that f of x has to equal a sine theta, right? So what do we have here? In our actual example, we have 3 squared minus and then 5x squared, right? So this means that we're going to let 5x be 3 sine theta. So let's write that down. Let's say let 5x equal 3 sine theta. Now, don't forget about the dx. In this case, we could get x by itself, but I could just take the derivative of both sides. I get 5 dx is equal to 3 cosine theta d theta, or dx is equal to 3/5 cosine theta d theta. Let's also remember what x equals here. X is the same as 3/5 sine theta, okay? So now that I have all this, remember, we're going to replace the dx with this, right? And everything else is going to be replaced with the substitution that we got, okay? So here's how we're going to write it. First of all, we have x squared over the square root of 9 minus, we have 5x squared here, right? And so this guy right here, 3 sine theta, is what I'm going to replace this 5x with. Okay, so let's see what happens. We end up with, now x is going to be 3/5 sine theta, right? So I have 3/5 squared sine squared theta over the square root of 9 minus, remember 5x is 3 sine theta, so it's going to be 9 sine squared theta. And then my dx is another 3/5 cosine theta d theta. Let's deal with what's under the radical here, okay? So this guy right here, I'm going to bring it over here just to see what happens. If I pull a 9 out, I get 1 minus sine squared theta. And then this becomes the square root of 9 cosine squared theta, which is the same as 3 cosine theta. Again, I'll leave the absolute value in for now, but we are going to get rid of it in this step since it is an indefinite integral. We don't need it. Okay, so this is actually equal to, let me start pulling some stuff out here, okay? So we actually have 3 cubed over 5 cubed because I'm combining the 3/5, all of the 3/5 on the top. And then we also have a 3 that we're pulling out from this 3 cos theta over here. So what we're left with is sine squared theta cosine theta, and then on the bottom we have cosine theta d theta. And we can go ahead and cancel the cosine thetas. So really, we have just the integral of sine squared theta. What about these 3's on the outside? One of those 3's goes away with one of those 3's on top. So we're really going to have 9 over 125. So this is what we have. Right, let me just make sure. Yes, it looks like that's our integral, okay? How do we integrate this? Remember, we learned how to do this in 7.2. We learned that if it's even, you need to use a half angle formula. So let me remind you guys of the half angle formula. It says that sine squared theta is equal to 1/2 minus 1/2 cosine of 2 theta. So then this is equal to 9 over 125 times the integral of 1/2 minus 1/2 cosine of 2 theta d theta. So what is the actual integral here? We haven't taken the antiderivative yet. It's going to be 1/2 theta. And then remember our linear trick, divide by the slope. And then the integral is sine of 2 theta plus c. Okay, so now what? Let me go ahead and just multiply that out just because we have this. 9 over 250 theta, and then minus 9 over 500, and then sine of 2 theta, and then plus c. Okay, remember, we cannot leave our answer this way because we need to make sure that we write everything in terms of our original variable. So let me remember our original substitution. Our original substitution was, let's use this right here. Remember, 5x is equal to 3 sine theta. So that means sine theta is equal to 5x over 3, right? So let's write this down. So if sine theta is equal to 5x over 3, we're ready to have a triangle here. There's our theta. We have 5x, and here we have 3, and so this is going to be 9 minus 25x squared. Which should match, by the way. Does this guy match what we started with? Yes, it does. Okay, so what would theta equal? We haven't seen this yet in an example, right? But we have a theta right here. So what would theta equal? Well, if sine theta is 5x over 3, then that means that theta is the arcsine of 5x over 3. So you use a trig function when you're left with theta at the end. An inverse trig function, sorry. So we're going to do that, 5x over 3. What about this next part? How can we write sine of 2 theta there if our triangle has a theta? So for this, you need to use the fact that we have a double angle identity, because this is 2 sine theta cosine theta. This trig identity is one that I recommend you memorize just because the double angle for sine shows up all the time. So sine of 2 theta is 2 sine theta cosine theta. So I'm going to write the answer like this, because if I multiply this by 2, so let me write it this way. I'll do the simplifying in the next step. So I have 2, and then sine theta, that's 5x over 3. And then cosine theta, what would cosine be? Look at the triangle. It's square root of 9 minus 25x squared over 3, and then plus c. We can actually simplify quite a bit here. Sorry, I realize now I wrote 9 over 250. I should have written 9 over 500, right? Okay, let's do some simplifying here. The 3's go away with that 9. And then the 5 and the 2, that gives you 10. And so 5 and the 2 cancel with this to give us a 50 on the bottom. And so our final answer, I'm going to write it in simplified form this time. I get 9 over 250 arc sine of 5x over 3, and then minus 1 over 50 times the square root of 9 minus 25x squared plus c. There is our answer. So again, the new thing that we saw in this problem was the fact that we didn't just have an x there. So don't forget that this, you've got to write it as something squared, and you really have to write it as two different squares, right? That's why I broke the 9 down as 3 squared, and I broke 25x squared down as 5x squared. Once you do that, the trig substitution becomes easy. So our next example is going to be a little more tricky. This is example 4. We're going to integrate the following. 1 over the square root of t squared minus 6t plus 13 dt. This is tricky because notice at the bottom does not look like one of the 3 forms, right? We're supposed to write it as a sum or difference of squares, and that does not look like that, right? So we are going to use completing the square to do this, okay? So let's write this here. This is going to be completing the square. So we're starting off with t squared minus 6t, and then what I do is I put this plus 13 to the side. And what we do now, and again, this is a reminder of stuff that you do in algebra, right? But what we're going to do is we're going to take this middle guy, 6, we're going to cut it in half and square it. So if you cut it in half, you get 3, and 3 squared is 9. And so you're going to add 9 to this. Now, of course, if you add 9 to something, you also have to subtract it. Otherwise, you are changing its value, right? And we're not allowed to just change it. So now we have t squared minus 6t plus 9, and then plus 4. The reason why we completed the square is that now this is a perfect square, isn't it? This factors to t minus 3 squared. You'll notice, by the way, that I can actually write this as the sum of 2 squares. Okay, so there you go. The whole point of this was to be able to write it in that form. And now that we've done that, that means we can rewrite our original integral so that it looks like this. T minus 3 squared plus 2 squared . Okay, so then what is our trig substitution going to be? Remember, if you have a function squared plus a squared, then that means we let f of x be a times tangent theta. So in this case, since we have t minus 3 squared plus 2 squared, then this means we're going to let t minus 3 equal 2 tan theta. Okay. All right. So what does dt equal? It turns out if you take the derivative of the left side, you just get 1. So that's dt, and that's going to equal to secant squared theta d theta. So what is our integral going to transform into? We end up with the top is just going to have our dt. The bottom is going to have the square root of, we have 2 tan theta, right? I'm going to replace this guy with this guy, right? That's t minus 3. And so we have 2 tan theta being squared, and so that ends up being 4 tan squared theta plus 4. Let's do this radical over here, right? Then this is going to become 4 times tan squared theta plus 1, which is the same as 4 secant squared theta, and then that's the same as 2 secant theta. So the bottom is really 2 secant theta. Let's do this on the next line here. Okay, so we had a 2 secant squared theta on the top, and on the bottom we have a 2 secant theta, right? I believe that's our integral. Yes. And so, of course, we can simplify this, right? The 2's go away, and then the secant theta goes away with one of those secant thetas. And so we're actually left simply with the integral secant theta d theta. So in order to do this integral, yes, this is something that we had to memorize from previously, right? So this is one of the integrals. This is equal to the natural log of the absolute value of secant theta plus tan theta plus c. Now we are not done. We need to use the triangle, right, to convert our thetas back to, what did we have? We had t, right? So let's use this relationship here. If t minus 3 was 2 tan theta, then doesn't that mean that tan theta is equal to t minus 3 over 2? Right? So all I did was divide both sides by 2. So let's do this on the next line, okay? So if tan theta is t minus 3 divided by 2, we can do a triangle. Remember, this is going to be the opposite, and this is going to be the adjacent, right? So this is t minus 3, and this is 2. So this is going to be the square root of t minus 3 squared plus 2 squared, which again, remember, this matches what we have here. Okay, so they should match. So we have the natural log of, what would secant be? Because right now what I'm doing is I'm trying to translate this using my triangle. So secant theta is, so cosine is 2 over that radical, right? Adjacent over hypotenuse. So I'm going to do hypotenuse over adjacent. So this is going to be the square root of, I could write it like that, but I'm also going to just keep things simple because I know that t squared minus 6t plus 13 is really what that equals, right? I can just write it back in the form that it was in the beginning of the problem, right? So it's going to be t squared minus 6t plus 13 over 2, and then plus tan theta plus t minus 3 over 2 plus c. Or what I can do is write this down. Now, I can write my answer like this. Okay. I want to show you guys something interesting, okay? One last thing. I actually want to show you guys that I'm allowed to do this. So, I want to show you guys something. The answer that I just got, let me do a little bit of further simplification, okay? Can't I write this as t minus 3 So what I did is I split up the ln, right? Isn't it true that the ln of a over b is equal to the ln of a minus the ln of b? That's just a property of natural log, right? Or any logs, really. But this can combine. If I take any arbitrary constant and I subtract ln of 2, I can just rename that constant to something else, right? So in other words, I could write my final answer this way. You don't have to do this, but it is a little bit cleaner. I could just write it this way. They are actually the same thing, okay? Because this thing plus an arbitrary constant is the same as what I have above plus an arbitrary constant. So if you want to write your answer this way, that's good. Or if you want to write your answer the way we boxed it over here, that's good too. Just understand that that 2 on the bottom actually can get absorbed into the constant, so it's less writing if you don't even put it there. Okay, that was definitely a tricky problem. So I want to go on to our next problem. This is number 5. We're going to do the integral of x squared over 3 plus 4x minus 4x squared to the power of 3 halves. This is going to be a very tricky problem. I want to do this example so that you guys see essentially the hardest problem that you can see during this lecture. I want you guys to see the hardest so that when you do your homework, it's really not that bad. So in order to do this, we're going to really need to manipulate this bottom, okay? Because that is clearly not a sum or difference of squares. So let's go ahead and do the algebra. Maybe we'll do this on the next page, okay? So here is our algebra, 3 plus 4x minus 4x squared, right? 3 plus 4x minus 4x squared. So I'm going to be completing the square here. So what does this equal? So here's the trick. The trick is actually to write it this way. So here's how I would do it. First thing we do, I wrote it in descending order, and what we need to do is we need to actually remove the negative 4 there. So if I take out the negative 4, I get x squared minus x, and then minus 3/4, right? So this is what I get when I take out negative 4. Next, we need to complete the square here. I'm going to leave this to the side here. So what we need to do is we need to take half of the negative 1, square it, and then add that in. That completes the square, right? So half of this guy is 1/2. And then you square it, you get 1/4. So what we're going to do is I'm going to add 1/4 to this, but then that means I also have to subtract 1/4. So here's what we get. We end up with negative 4 times x squared minus x plus 1/4, and then minus 1, right? Why do we get minus 1? Well, 3/4 and 1/4 give you 1. Now, we're going to do an interesting trick here. We actually want to get rid of this -1, so we're going to break it out by multiplying these two together. So actually, we can write it this way. And finally, we can factor this inside. Remember, we did this so that we could factor it, and this factors to x minus 1/2 squared. And then plus 4, which is the same as 4 minus 4 times x minus 1/2 squared. Okay. Okay. So that was a lot of work, but we were able to write it as something times something squared. And in fact, let me just go a little bit further, right? Can't I write it this way? So what I can do is I know that this 4 right here is the same as 2 squared, and then I can actually put the 2 in there. So here's why. If I have 2 squared times x minus 1/2 squared, this is the same as 2x minus 1 squared. Why is that? Because remember, a to the m times b to the m is ab to the m. All I'm doing is I'm multiplying the like bases together. Okay, and so we have, I'm basically trying to write it in a comfortable form here, and so we end up with this. Or if we want to really finish up and write it as nicely as possible, this is how we can write it. And I do recommend you check. You can always check with algebra and make sure that if you actually simplify that, you get back to what we started with. So let's go back and write it like this. So 2 squared minus 2x minus 1 squared. So we get 2 squared minus 2x minus 1 squared, and all of that is to the 3/2 power. Okay. All right, so we're ready to do our trig substitution here, okay? Remember, if we have a squared minus a function squared, we know that we let the function be a sine theta, right? So that means that our function 2x minus 1, so I'm going to say let 2x minus 1 equal 2 sine theta. Another way to write this is if we were to solve for x, we actually get, let's see here, 2x is equal to 1 plus 2 sine theta, or x is equal to 1/2 plus sine theta. Okay, all of this is important because we're about to substitute in, right? So what is dx though? We should also do dx. So dx is equal to just cosine theta d theta, right? I got that really from this guy here. What are we going to do? We're going to now do our substitution, okay? Remember, the dx is going to become this. And actually, let me back up here. I want to use this expression, right? There's a reason we did it over here, the completing the square. So remember, dx is going to become that, And for the x squared at the top, we're going to use this guy. You know what? It might be better to write this as follows. I'm going to divide everything on the top line by 2. So that actually gives me 1 plus 2 sine theta over 2. Let me write it that way. Okay. The reason I want to write it like that is because this is going to be easier to plug in. Remember, I need to plug this guy. I need to plug this guy for this guy, right? It's going to be I need to square that. So let's go ahead and square that, and that's going to go on the top. So that's going to give us 1 plus 2 sine theta. I'm going to square that. The bottom is going to have a 2 squared, so let me actually pull that, or let me write it like this. I'm just going to have a 2 squared down here. So that's the x squared part. Now I need to replace the 2x minus 1 with 2 sine theta. So then I have 2 squared minus, let me write it this way. 4 minus, remember I'm replacing 2x minus 1 with 2 sine theta, so it's going to be 4 sine squared theta, and then all to the 3 halves. And then my dx, don't forget the dx, cos theta d theta. So this is my new integral. Yikes. Looks pretty bad, and I'm not saying this is going to be an easy integral, but at least we're going to be able to solve it, okay? Okay. So can we do some simplifying? Absolutely. All right, so that's what we're about to do. Before I actually square that thing out, I'm going to keep writing it down. I want to see what we get here. Let's on the next line deal with this 4 minus 4 sine squared theta, right? So this guy right here, 4 minus 4 sine squared theta to the 3 halves is equal to 4 times 1 minus sine squared theta to the 3 halves, which is the same as 4 cosine squared theta to the 3 halves. Remember what 3 halves power is. It's taking the square root of something and then cubing it. So what do we get? The square root of that is 2, so we actually end up with 2 cubed cosine cubed theta. All right, so here's what we get. Let's write this on the next line. I want to make sure I don't make a mistake when I copy this over, right? So we have the integral of, let me do the top first, 1 plus 2 sine theta squared. And then I have a cosine theta d theta. And then I have a 2 squared down here, but I also have a 2 cubed. So what would that be? 8 times 4 is 32, right? So I have 32 cosine cubed theta on the bottom. (32 cosine cubed theta on the bottom. Can I simplify? Absolutely. I can cancel that cosine with one of those, and that's going to become a cosine squared, right? And let's go ahead and actually multiply that thing on top, okay? That thing on top is, if I were to square this thing out on top, I get 1 plus 4 sine theta plus sine squared theta. And then on the bottom, so I'm going to pull the 32 out. And then on the bottom, I have cosine squared theta. And then I have d theta. this is a tricky integral, okay? It's tricky, but it's really not as bad as it seems if you look at it piece by piece. If you try to do this integral in one step, then you're going to have trouble, okay? Now, watch what I'm going to do. I'm going to write it like this. So I have the integral of 1 over cosine squared, which I'm going to write as secant squared, plus I have, I'm going to leave the 4 inside just to be easy here. So I have sine theta over cosine squared theta. Let me write it like that. And then my third integral, what's sine squared over cosine squared? It's tan squared, isn't it? I wrote it as 3 integrals because actually this makes my problem much easier to do. Okay. Now, how do I do this? Something important to notice is that it may not seem like it, but this last integral and this first integral can actually be done together. And the reason why is that this guy, tan squared is the same as secant squared theta minus 1, isn't it? So if I'm adding those two together, what that means is I can actually write it like this. I can have 2 of these plus 4 of these, and then I have the minus 1 here, right? Now I do each one piece by piece, and they're actually not hard to do on their own, okay? So for the first one, what's the antiderivative of secant squared? We should know this, right? It's just tangent. The derivative of tangent is secant squared, right? So we end up with, first, 2 tan theta plus. What about the next one? Let me look at this guy, and I'm going to look at it up here. Can't I just, for that guy, and let me do this. Can't I, for this guy, just let u equal cosine theta? Because the derivative of sine theta, it appears on top, right? So this means that du is negative sine theta d theta. And so my integral is going to become negative 4u to the negative 2 du. Okay. So when I actually integrate that, I get u to the negative 1 over negative 1. So the negatives are going to go away. So I get 4 over u, which is the same as 4 over cosine theta. Okay, which actually is the same as, I guess I could write it this way, right? That's the same as 4 secant theta, isn't it? Okay. So 4 secant theta. Finally, minus theta. Now, I could write my answer like, I cannot leave my answer like this, sorry, because I cannot leave theta in my answer. Going back to the beginning, remember that theta was my second variable. My first variable was x, right? And so this is our relationship here. If 2x minus 1 is equal to 2 sine theta, let's write that over here. 2x minus 1. Yeah, let me start over here. If 2x minus 1 is equal to 2 sine theta, then this means that sine theta is equal to 2x minus 1 over 2. So this is 2x minus 1, and this is 2. So remember, this is going to be 2 squared minus 2x minus 1 squared. And again, this should match what we started with. 2 squared minus 2x minus 1 squared, right? So that's good. But I am going to use this form of it, right? I'm going to use that form of it because that is the form that we were given in the beginning of the problem. So 3 plus 4x minus 4x squared. 3 plus 4x. 3 plus 4x minus 4x squared. So I need to translate this, okay? So I'm going to distribute the 32 now, just so it goes into my answer and I have less parentheses floating around. So I have 1 over 16 tan theta. And then I have plus 1 over 8 secant theta. And then I have minus 1 over 32 times theta, and then plus c. But I can write what all of those are according to my triangle. So I have 1 over 16 times tan theta. 1 over 16 times tangent, remember, is opposite over adjacent. So that's going to be 2x minus 1 over that radical, right? So 2x minus 1 over that radical. And then plus 1/8 times secant. Remember, secant is going to be hypotenuse over adjacent. So that's times 2 over that radical. And then I have minus 1 over 32 times theta. So what's theta going to be? Theta is equal to the arc sine of 2x minus 1 over 2. Okay. So how do I write my final answer? I do want to write this in a slightly nicer way just because I see an obvious way to simplify here, because these two almost have the same denominator, don't they? These two fractions, this guy has a 16 and the other guy has an 8, so I'm going to multiply by 2 and multiply the bottom by 2 also. So now I can combine these. My final answer becomes, I have 2x minus 1 but then plus 4, so that's 2x plus 3 over 16 root 3 plus 4x minus 4x squared, and then minus 1 over 32 arc sine of 2x minus 1 over 2, and then plus c. That was a very tough problem, okay? You will probably not see very many problems this difficult. You know, you won't see anything this difficult on an exam, I can promise you that. But, you know, maybe you'll have 1 or 2 on the homework that are difficult. You know, I wanted you guys to see at least one really, really hard problem. And to me, the hardest part about this is the fact, well, there's lots of things, right? The first thing was this completing the square was pretty complicated. So understand that we have to sometimes do some interesting factoring tricks in order to make the completing the square work out. And then even after that, the integral was quite complicated and we had to break it up into 3 pieces to be able to solve it. Okay. But that problem was a good problem. It illustrated a lot of stuff. Okay, so for our last example, I want to illustrate something here. So this is going to be number 6. We're going to do the integral of x over the square root of 1 plus x squared. dx. Now, this is a lot easier than the one that we did previously, right? So I'm going to go ahead and just solve it. It should be pretty straightforward here. We know that for the trig sub, we know that x is equal to, in this case, just something simple, tangent of theta. And dx is equal to secant squared theta d theta. So we have tan theta over square root of 1 plus tan squared theta. And then we also have the dx is another secant squared theta d theta. So let's take this guy over here. And I'm doing this example for a reason. You guys will see very soon, okay? So if I take the square root of that, then that's the square root of secant squared theta, which is just secant theta. So my answer is, or not my answer yet, but this is tan theta secant squared theta d theta over secant theta. Cancel this guy on the bottom. And so we're integrating secant theta, tan theta. Hopefully we remember that that is just secant theta plus c. And we need our triangle to change back, right? So if x is equal to tan theta, this is really an x over 1, isn't it? So we can draw our triangle. And that means this is an x, that's a 1, and this is a 1 plus x squared underneath. So secant is just going to be square root of 1 plus x squared over 1 plus c. Why did I show this problem? I mean, it wasn't the hardest one we did, right? It was pretty simple, actually. But here's the thing I wanted to show you guys. The question is, did we need to use this method? So let's go ahead and call this method 1. Because there is another way of doing this problem, and in fact, the other way is going to be a lot easier. So let me rewrite the integral. Remember, the integral, this will be our method 2. The integral was x over the square root of 1 plus x squared dx. So if you showed this to a Calc 1 student, they might say, wait a minute, can't I just do a u sub and let u equal what's in the radical? Because its derivative is 2x and it appears up there, right? I have an x up there. So why not just let u equal 1 plus x squared? So let's see, du is 2x dx, or 1/2 du is equal to x dx. And so, what do we get here when we replace it? We get u to the negative 1/2. I have a 1/2 out here as well, right? And then use the power rule. This is just going to be u to the 1/2 divided by 1/2, so that goes away. So it's just u to the 1/2 plus c. Or if you replace u back, you get square root of 1 plus x squared plus c. This is definitely easier, right? This is much easier than having to do the whole trig sub and do the triangle and everything, okay? So why did I want to illustrate this problem? It isn't just about doing these problems and getting them right. It's about using the easiest technique that we know, because the harder the technique is that you choose, the more likely you are to make a mistake. So tip, always look for the easiest method to use. In this case, a u substitution was the easiest method. So just because you can solve it using a technique, it does not mean that you should use that technique. Or put it another way, a lot of times these problems can be solved with more than one method. So it's good practice to just try your best to not make your life any harder than it already is. All right, everybody, thank you for watching. I know this video was long, but this was a challenging topic, and I wanted to make sure we did lots of examples. Thank you so much for watching, and hope it was helpful.